All right, I want to do an example here of using implicit differentiation. I want to do the following problem. Find the equation of the tangent line to this graph at the point 1, 1. So it is useful to note that if I plug a 1 and a 1 in here for x, this is a 1 minus 3 plus 1. So that's a negative 1 on this side, and this is a 4 plus 1 minus 6, so that's a negative 1 on this side, and so the negative 1 is equal to negative 1, and so yes, 1, 1 is on this curve, whatever the curve looks like. I don't know if you have any idea what it looks like, but I could come up with some ideas, but they're just kind of foggy ideas what the graph of that might look like. But still, it looks like something, and at the point 1, 1, you know, where whatever it looks like at the point 1, 1, the curve passes through there, and there should be a tangent line, and let's find it. Okay, so what I do is I'm going to implicitly differentiate. I'm thinking of y as some function of x. So all of this stuff is one big old function of x. All of this stuff is one big old function of x. And I'm going to take the derivative of the left-hand side. With respect to x. I better be careful because the left-hand side wasn't x cubed, it was x squared. It's y cubed, but x squared. And that's going to be equal to the derivative of the right-hand side. Okay, so here we go. This is a sum or difference of a bunch of things. I'm just going to take the derivative of each piece. I'm taking the derivative with respect to x here. So this is x squared, so the derivative there is just 2x. Here I've got negative 3 times x times y times. Look at all those times. That's a product right there. I've got x times y. The multiplying by 3, I'm going to just put that out in front because when you're taking the derivative of a constant times something, the constant just gets multiplied out in front. So I'm going to leave that minus 3 there and focus on the x times y. This is a product of x and y. So the derivative is the x times the derivative of y plus the y times the derivative of x. Right? And all these derivatives are with respect to x. This right here, the derivative of x with respect to x is just going to be a 1. Right? That's just a 1 right there. Okay. But the derivative of y with respect to x, it's like, well, I don't know what y is. If I did, I'd take its derivative. That's what I need to do right there. Plus, so that was, I did this one, I did that product rule, and then I have a plus y cubed. So the derivative of y cubed, if I just write 3y squared, that's the derivative of y cubed with respect to y. I don't want it with respect to y, I want it with respect to x. So the chain rule says multiply by the derivative of y with respect to x, right? This is something in parentheses raised to the third power. The derivative is 3 times that something squared times the derivative of what's inside. Well, the what's inside is y, so there's the times the derivative of what's inside. So, actually, I wrote an equal sign out in front here. I don't like that equal sign out in front. This is the derivative of the left-hand side, and it's got to equal now the derivative of the right-hand side. So I'm looking at the right-hand side. The derivative, it's just a sum of 3 things. I'll take the derivative of each piece. The derivative of 4x with respect to x is just 4, plus the derivative of y with respect to x. Well, that's the derivative of y with respect to x. If I knew what y was, I'd take its derivative, so that's what I want right there. And then minus the derivative of 6. Well, the derivative of 6 is 0. So now I need to solve for dy dx. Now I see 3 dy dx's here. There's one there, one there, one there. Actually, if I look at my original equation, there were 3 y's in it. Y, y, y. It should always work out that way. However many y's that you see, at some point you're going to take the derivative of that y, and it shows up as a dy dx. So if there were 3 y's to start with, there better be 3 y's down here. And now I'm going to do this. Let's see, I'm going to distribute that through. So let's rewrite this. I've got 2x minus 3x times, actually I'm just going to write that as y prime, minus 3y times 1 plus 3y squared y prime equals 4 plus y prime. And so the way I'm going to solve now is I'm going to get all the y primes on one side and all the stuff that doesn't have y prime in it on the other side. So, so here we go. I've got a negative 3x times y prime. I've got a plus 3y squared times y prime. And if I subtract this one over, I've got a minus y prime. Now the 4 is already over on this side of the equation. I'm going to bring this 2x over there as a negative 2x. And I'm going to bring this negative 3y over as a plus 3y. And then everything on the right, sorry, everything on the left now has got a factor of y prime in it, so factor it out. Y prime times negative 3x plus 3y squared minus 1 equals 4 minus 2x plus 3y. And then you can divide by this to get the y prime by itself. So I have y prime equals 4 minus 2x plus 3y divided by, I'm going to change the order just a little bit just because I like to put the positive 1 out in front here. So 3y squared minus 3x minus 1. Okay. Now one thing, so this is the derivative. I'm going to use this now to get the slope of the tangent line. But one thing to notice is that when you're doing this implicit differentiation is that when you run across a y, as you're implicitly differentiating, each time you run across a y, you'll get a y prime that pops out, or a dy dx that pops out from the chain rule. The thing is, you'll never get this thing squared, or you'll never get the square root of y prime, or you always just get it once multiplied out there, just to the first power. So when you're then solving for it, it's really pretty easy because you get all those factors that have a y prime in it and factor it out. You're never going to have y prime squared that you're going to have to mess with. It's just always just y prime to the first power. So you factor it out. There it is. And then you can divide by whatever that stuff is. And it generally is pretty easy to solve for it once you've implicitly differentiated there. Then solve for y. So now, now that I've got this, I can say at the point 1, 1, y prime, sorry, this looks funny. Let me move this down a little bit. So at the point 1, 1, y prime equals, I'm just going to plug in my x and y values. So I've got 4 minus 2 times 1 plus 3 times 1, all divided by 3 times 1 squared, minus 3 times 1, minus 1. So I've got 7 minus 2 is 5 on the top and minus 1 on the bottom, so negative 5. So y minus 1 equals minus 5 times x minus 1 would be the equation, or an equation, for my tangent line. I'd just as soon leave it like this because I can see the point that it goes through. I can see the slope. You could multiply it out and collect some like terms if you wanted, but I like it that way. One thing I want to do is I want to actually look at a graph and see that this works. So just a moment and I'll switch to the graph. So I've asked my my graphing calculator here on the iPad to draw the graph of this equation here, and it looks like apparently it's got two pieces. It's got this kind of loop up there and then something down here. And I noticed that the point 1, 1, yeah, right there, the point 1, 1 is in fact on the curve. It's got a fairly steep negative slope at that point. And I also have the equation of the tangent line that we just got here with a slope of negative 5 going through the point 1, 1. And if I show that line, actually it looks pretty dang good there. It passes through that point, seems to be just tangent to the blue curve. So I'm pretty happy, right? There you go. There's an example of implicit differentiation used to find the slope of a tangent line at a point on a curve.